All right, welcome back, everyone. Get ready because today we are leaving the world of stretching and pulling behind, and we are jumping headfirst into the world of slicing and shearing. It's going to be fun.
Okay, so let's just dive right into this. But before we get into the new stuff, let's get our brains warmed up with a really quick recap of our last explainer on Hooke's law.
So, if you remember, we figured out three main things. 1. Hooke's law is basically the golden rule for predictable stretching. 2. A material's stiffness has a score, and we call that the modulus of elasticity. And 3. That weird skinny effect when you pull on something, that's all thanks to Poisson's ratio. Pretty straightforward, right?
Okay, but here's the big question. What happens when you're not pulling on something? What happens when you're pushing from the side? Or even better, what happens when you try to slice right through it? Well, that is exactly what we're tackling today as we dive deep into section 1.6, shear stress and strain.
And listen, here's my promise to you. We are going to make this stuff simple, fun, and totally understandable. I'm talking so clear that by the end of this, you'll be seeing shear forces everywhere. Seriously, from a simple pair of scissors all the way to how bolts hold a massive bridge together. So here's our roadmap for today. We're going to go from stretching to slicing, meet shear stress and its partner strain, see how they're related through a familiar law, check out some real-world action, and then finish up with a quick quiz. Let's get to it.
All right, section 1. Let's start by really nailing down the difference between stretching and slicing. You know, it really just all boils down to one simple thing: the direction of the force.
So check this out. On one hand, you've got normal stress. Remember that? The force is perpendicular to the surface. It's like you're pulling a rope straight apart. But shear stress, that's a whole different beast. The force is parallel to the surface. The best way to picture it, imagine a deck of cards. When you push the top card off, that sliding, slicing motion, that is shear stress in action. It's not about stretching, it's about sliding.
Okay, so let's get a formal definition here. What exactly is this force, shear stress, that wants to cut things in half?
This image is just a perfect example. What you're looking at is a bolt connecting two parts. See those forces P? They're trying to pull the plates in opposite directions. Now look closely at the bolt itself. The forces are literally trying to slice the bolt right at those two spots, MN and PQ. It's like a giant pair of scissors trying to snip it. That is a direct shear force, and it's a super common way for bolts and rivets to fail.
So how do we measure this? Well, just like with the pulling forces, we have a formula. We call the intensity of this force shear stress. That's the Greek letter tau right there. And the formula? It should look pretty familiar. It's just the shear force, which we call V, divided by the area, A, that it's acting on. Simple as that. It tells you just how concentrated that slicing force is.
Okay, so we've got the force, but what does it do to the material? How does stuff react to being sheared? This is where it gets really cool. It's not about getting longer, it's all about changing shape.
Check this out. On the left, we've got a perfect little square element. Now, when we apply shear stress, look at what happens on the right. It doesn't get longer or shorter, it deforms. It turns into a rhomboid. All the side lengths are the same, but the angles have changed. It's been distorted. That's the key difference.
And you know what? That change in angle, that amount of tilt or distortion, it has a name. We call it shear strain, and we use the Greek letter gamma to represent it. It's just a measure of how much that original 90-degree right angle has changed. So, remember good old Hooke's law? Well, if you thought we were done with it, surprise, it's back for a sequel. There's a version of Hooke's law just for shear, and it's awesome.
Just look at this comparison. It's basically the exact same idea. For tension, we had sigma equals E times epsilon. Well, for shear, we have tau equals G times gamma. Stress equals some stiffness constant times strain. This new constant, G, is called the shear modulus. Think of it this way. E was the material's stiffness against being stretched. G is its stiffness against being sliced or distorted. Same concept, different direction.
Okay, theory is great, but let's see where the rubber meets the road. Where do we actually see this stuff out in the real world? Let's check out a couple of examples.
You've used a hole punch on a piece of paper, right? Well, you were creating shear stress. You're literally slicing a circle out of the paper. This is the exact same thing, just on a much bigger scale. Here, a massive 26,000-pound force is being used to punch a hole in a steel plate. The plate isn't being stretched, it's failing in shear. And get this, the average shear stress in that steel plate right as the hole is punched is 44,200 psi. That's over 44,000 pounds of force on every single square inch. That is a mind-boggling amount of slicing pressure. Here's another cool example. You ever see those big rubbery pads under a bridge or a big piece of equipment? They're called bearing pads. When a force pushes on them from the side, they don't really compress. They lean. They distort. That little bit of sideways movement, is pure shear strain. The whole pad is just shape-shifting to absorb the force.
Okay, we've covered a lot of ground. Hopefully, it's all starting to click into place. So let's lock in what we've learned with a quick quiz. You ready for this? All right, just 3 questions. Number 1, is shear stress a parallel or a perpendicular force? Number 2, what does shear strain, that little gamma symbol, actually measure? And finally, number 3, what's the name of that stiffness score against slicing? Go ahead, lock in your answers.
All right, let's see how you did. The answer to number 1 is parallel. Remember, it's a sliding, slicing force. For number 2, shear strain measures the change in shape, specifically that change in angle. And for number 3, our stiffness score is the shear modulus, or G. Hey, if you got all 3, you're a shear genius. Nice work. Okay, so if you forget everything else, just remember these 3 key takeaways. First, shear stress is a slicing force that's parallel to the surface. Second, shear strain is the change in shape, the distortion that the stress causes. And third, Hooke's law for shear, tau equals G gamma, is the simple rule that connects them, with G being the material's resistance to that slicing. But all this leads to the really big question, right? Now that we know about these stresses, what do we do with them? How do we design things that can handle them? In other words, how much is too much? That is the critical question we're going to answer in our very next explainer, where we'll dive into section 1.7, allowable stresses and allowable loads. So, if you found this useful, do me a favor and hit that like button. If not, the dislike button is right there too. It helps us improve. And of course, leave any and all questions in the comments below. Make sure you follow so you don't miss what's coming next. I'll see you then.